Hello, everyone. I'm Lara from eProsima, and today I'm going to host this embedded working group. In the document I'm sharing and the document which is also in the chat, please write down your name on the attendance list. Also, you can add some topics which you wish to discuss to the miscellaneous section. Thank you very much. As a recap, let's have a look to the last agenda of the embedded working group in June. Eduardo Pons showed the Vulcanexus framework, which is the all-in-one ROS2 toolset, and one of the goals is the integration of micro-ROS into ROS2 networks. Then Javier Paris showed us a use case about a drone swarm in the cloud, and it was based on the DTS router, which is the technology that allows seamlessly communicate geographically distributed edge devices. And finally, our colleague Pablo Garrido talked about the latest release of micro-ROS Humble. And for today, we have a very interesting agenda. And first of all, I want to mention that we'll be at the ROScon in Japan. And well, we are very, okay, sorry, it's another person here, which is a chance to spend an extraordinary 2 days learning from and networking with the ROS2 community. We'll get tips and tricks from experts and meet and share ideas with fellow developers. So if you got the opportunity, you must join to this event. On the ROScon, we'll be hosting 2 interesting talks. Raúl Sánchez, our colleague from eProsima, will be talking about how to monitor the ROS2 network. He will present FastDTS Monitor, which offers a graphical interface to monitor everything in real time, all the entities and other networks and DTS statistics and parameters. And our other talk is from Eduardo Pons from eProsima also, and he will talk about how to filter the ROS2 content. In this talk, he will present a new feature and a simple demo of how to filter the contents of a topic and saving bandwidth. So now, okay. And we'll be also, sorry, I was forgetting, we'll be attending next interesting talks. We'll be at the Bosch meeting that they will talk about automotive and micro-ROS. The talk is Micro-ROS Goes Automotive by Ralph Lange and Jan Staschulat, who is with us today. We'll be attending also the Microsoft talk related to IoT, Microsoft ROS Meets IoT by Benjamin Cabet. And another interesting talk will be Micro-ROS 2, yet another runtime environment onto embedded devices by Hideki Takashi from Tokyo's University. And for today, we have prepared an interesting agenda. And our first talker is Jan Staschulat from Bosch, which will talk about discussion about advanced executor concepts in micro-ROS. Then Bartolomé Jimenez from Capra Robotics will talk about Microsoft at Capra. And finally, Tanmay Deshmukh from Coalescent Mobile Robotics will talk about retail automation. So now is the turn of Jan Staschulat. Hi, Jan, are you ready?
Yes, hello. So
Hello.
I'd like to share
welcome.
my screen.
Yes, of course.
Let's see. Okay. Okay. So can you see my screen?
No.
I think you should stop sharing, Lara.
Okay. Okay, now. Sorry.
Right now, Jan.
Now you can see?
Yes.
Okay.
Okay.
Now it's sharing, I guess.
No, we can see you, but not your screen.
Okay, then I try. Share.
No.
Now we can see it.
Now
No.
something's happening.
Yes, perfect.
Okay. Okay. I would like to start, or I would like to give some ideas, some concepts that we have made, or I have made, about the architecture of the micro-ROS execution management. And the short presentation, I have 15 minutes. I would like to give a short motivation, then describe features that would be very interesting for a generic micro-ROS executor, show some architecture design for those executor features, current limitations of the micro-ROS client, and possible next steps. So the current architecture, let's say, I like to start differently. So for real-time applications, you have different requirements. So typically you have on a high level, you have maybe subscribers to do control applications, actuation control, which have real-time requirements, but you also have best effort. And what you would need is, or would you like to have, you like to have some prioritization for those callbacks. Some other interesting feature that ROS2 has, but micro-ROS does not, is a thread pool. So typically, this allows for pipelined execution where you have high frequency message data coming in, but a relatively long processing time. And with the thread pool, you could manage this. And of course, if you would have multi-core, then you could have multiple threads per core. And the third aspect is non-POSIX operating system. And what we mean with this is that in automotive, typically AUTOSAR-based systems are used, which are strictly periodic which use strictly periodic task scheduling, which is something very different from threads, which always run into completion or waiting. And that scheduling is not easily that is not supported by micro-ROS, but the use case of using micro-ROS in automotive is very interesting. So therefore, we have been thinking about how can we integrate all these different features like prioritization, a thread pool like in ROS2, and also non-POSIX, so supporting non-POSIX operating systems into a generic micro-ROS executor. And just to give a short recap of the executor design in ROS2, it has 2 steps. So when there are messages on DDS, first you need to create a wait set to tell the underlying middleware what are you waiting for, and then you get information about which messages are available. And then in the second step, you take that particular data, and then you can call the corresponding callback for that data. And in the single-threaded executor in micro-ROS, it's shown here in different diagram, where first we create a wait set, then call RCL wait, where's communication with a DDS or micro-ROS or micro XRC DDS. And for all handles that are available, you will take then that message, and then as a final step, you call the callback of this particular handle. And handle here can be a subscription, a service, client, and so on. We have been thinking about how can this be extended to support prioritization. And one idea is that the actual execution of the callback will be done in a worker thread, and the worker thread can be created with certain scheduling policies like pthread create, which supports different scheduling parameters like priorities in the simplest case. And the executor itself then only fetches or only asks for new data from the XRC DDS by RCL wait, and then checks if that particular worker thread is ready, so can process this call, and then only then takes that message and then copies, or let's say makes a handshake between the worker thread, and the worker thread essentially waits for this new data and calls the callback and then is ready again. So this dispatching executor we have implemented in a NATEX in a particular branch about a year ago, and I'm about to want to merge this branch. But I would like to go on, and that is a generalization of this concept would be not to have one dedicated thread for a particular subscription, but also to have a generic thread pool where you have, let's say, M threads, and then whenever new data comes in, the next available thread will just take over that data, and that's kind of shown here. Another very important aspect what we have been working on at Bosch is to port micro-ROS to AUTOSAR-based platforms. And there the problem is that in AUTOSAR you have fixed periodic task scheduling seen on the right side, where then it's difficult to map these callbacks I mean to a particular task, because some callbacks, as the rate of certain callbacks might be very high, so you have to attach the callback to a particular period, and other callbacks might be running very long, so they also cannot be put into particular tasks. So this has to be all mapped, and we found that this idea of this dispatching executor fits also very well to this context. So as shown here on the left side, this is a normal way of executing micro-ROS callbacks. So to say there's a handshake with the DDS, then you take one message, you execute the callback, take the next message to execute the callback, and what is done here is that the callback is distributed, is hard-coded, so to say, to a particular task running at a certain frequency, and the executor task itself will just take the message from the DDS and dispatch it, so to say, to a particular task, which is also shown here in this graphics that corresponds that I have a periodic task for every handle, and the message is taken out of this. I know it's a lot of detail, but I would like to spare you with this feature comparison. More importantly, we have been thinking about all these different features. We have different ideas because how to integrate it into a generalized micro-ROS executor, because we think all these features would be very beneficial for the community and for the users. And we ran into a couple of issues or a couple of limitations of the current XRC DDS. Of course, we know that the XRC DDS is thread safe, but it does not provide currently a good API for assigning priorities or something like a thread pool. And we have also looked briefly into the implementation. So there's a single mutex for the RMW weight, and that could potentially block when a lower priority thread has this mutex and a higher priority thread wants to take it. It has to be looked into more detail. And I made an experiment with just 2 threads, this typical round ping pong example, measuring round trip times, which increase in from 2 milliseconds for a single threaded case to 400 milliseconds for multi-threaded case. And so there might be some other things that needs to be looked at in more detail. And the second thing that hinders us for the dispatcher executor is that we need to have a handshake mechanism to know when a thread is ready, either in the thread pool or in the dispatcher executor, to know when to take messages. So now it's not only when new messages are available from DDS, but also when the computing device, so to say the thread, is ready, we take messages from DDS. But currently the implementation of the guard condition is simplified in micro-ROS client that does not immediately return when a new message is received or when it is triggered. And this functionality we need in this dispatcher executor. Another thing I would like to touch on is for the non-POSIX case, there's some initialization between the client and the agent that uses blocking calls to set up the handles like nodes, publishers, and subscribers, which is fine for a POSIX-like operating system, but this needs to be adopted. And we have developed a prototype that we will also present in the ROScon conference in October next month. Possible next steps, and not probably much more than 50 minutes, but we would like to refine the architecture design of this generic micro-ROS executor to support an API for prioritization, a thread pool, and non-POSIX operating system. And we need to dig deeper and identify these bottlenecks and propose improvements for the XRC-EDDS middleware. For example, to have a guard condition that returns immediately when it's triggered. To have also a data sharing concept for a thread pool. What I mean with this, when we look into the thread pool implementation of ROS2, it dynamically allocates always new data when and the new thread takes a new message, because it could happen that the assigned data for a subscription is already taken, so the thread is running, and next message comes in, and then the question is to which data location will then RCL take put this new data. And dynamic memory allocation is certainly not something that we would like in micro-ROS, so we have to think about a concept there as well. And we would like to bring the non-blocking calls for the initialization of the client in the agent somehow in the XRC-EDDS middleware. And for all this, we would need, we would like to have a more detailed discussion with eProsima and also with the community. Maybe the people who are also in this call can share their maybe their wish list for other features, or they say, okay, this is exactly what we would like in micro-ROS, or add some other use cases. And I just want to say we put a lot of effort into coming up for a design for this for an executor that's much more sophisticated and has similar features like ROS2, like the thread pooling, but also supporting non-POSIX systems which are useful in automotive context. And now the question is how we could move forward and move those obstacles away. So it's kind of more also steering discussion, also outside of this, continuing this discussion maybe in an issue or something like this. And with that said, I'm open for suggestions or comments. Yeah.
Thank you very much, Jan. I think that this is really interesting. The point about non-blocking call for initialization, I have been thinking, and in fact, I have a quick prototype on that, and I think that this is completely possible, like saving the state and saving the initialization parameters of the micro-ROS entities. And I guess that in the previous slide you mentioned something about interlocking between high and low priority threads, and because of the single mutex in the middleware in XRC-EDDS. And I think that this is something that will happen always if you don't have a system with a priority inversion. But in general, I guess that in the middleware level, we should be like thread safe, that we should not handle priorities or something like priorities. Maybe if in the higher layers, maybe in the RMW or in the RCLC or something like that, we can provide APIs for setting, like priorities for workers that are handling the callbacks and all these kind of things. But the middleware in general is just I think that should be thread safe. But okay, just quick thoughts. But I mean, we should talk about this because this is really interesting.
Yeah. Basically, I wanted to open up, so to say, our ideas and to come to to say that we have a couple of ideas, a couple of concepts, and now I would like to have start a more detailed maybe discussion about this. Maybe we can put this offline, or other people who are also interested are most welcome to join, or also share their requirements for real-time or non-real-time APIs.
The basic message that we developed many concepts in the last years and have prototyped for many things, and now it's the idea to come to let's say well architectured executor that fulfills all this, to avoid that we have later 3 different implementations. And on this non-blocking, we also have from the master thesis, you know them, Pablo, which has been also presented in June's meeting or May's meeting. We also have a prototype for that, and can also share it. That's
Okay, thank you.
And of course, it will also affect the upper layers. That's then our part also. Ideally, would be our wish, but that will be a longer attempt to bring these changes to RCL and it's RCL and RMW even into mainline ROS, because at the end, let's say if you have the non-blocking version, you can always build the blocking version by just calling all the functions in a simple function in sequence. So I think it can be refactored without changing the API for the current RCL CPP, RCL Pi, and so on.
And this is very interesting, and actually I'm going to be presenting afterwards. We actually use a lot of threads, and we have different nodes running in different threads, and we actually, the middleware runs on only one. We share a lot of threads, and we share one middleware. So it's very interesting. One thing that I'm curious, wouldn't it be possible, instead of having so many executors everywhere, to try to push it to the RCL level? Because we have RCL, like we have executors in a lot of places. RCL CPP, now in RCL-C, I think we have all these real-time executors. I'm a little bit curious, like maybe sometimes concerned about the fact that we're putting so many specialized executors that maybe could be shared actually for people that are working with RCL CPP to be able to use them. Just also to consider that.
I know that this has been a discussion also with William Woodall, so the maintainer of RCL and RCL CPP, and he said it's not possible because, let's say, then you directly use the standard C++ API for creating threads in the multi-threaded executor and so on. I think in fact it's really complicated. The other point is you pass function pointers inside, and they look very differently. So the common part will be so small that we consider this as very difficult. But I have to say, in RCL CPP level, I know there's this multi-threaded, single-threaded, static single-threaded, but they all are derived from the same parent class or abstract class. So a lot of the functionality is already centralized. So if you look in the multi-threaded executor CPP file, it's I think 100 lines of code or something like that. That's really small, and same applies to single-threaded and static single-threaded.
Okay.
Jan, something to add?
Yeah, I mean, there was always a discussion why why don't you have? I mean, you have RCL, right? I mean, why don't you have also the executor in RCL, but have it in RCL CPP and RCL Pi? And the main reason was that you would like to use all the features that you have in that language. So, for example, in RCL CPP, you would like to use, let's say, lambda expressions and all that stuff as a callback, and also member functions and so on. And that's then much more difficult if you have only a C API. And that's why they have chosen to have the executor itself in the language front end.
Okay, so very interesting. Does anybody else has any question?
One question, perhaps to you, Pablo. You can answer this probably directly. Did we get this correct, that we have in the RMW adapter from micro-XRC EDDS this one mutex?
Well, in general, the middleware, the micro-XRC EDDS library has one mutex for protecting the whole API, and then in the RMW we have some more of them. I think that we should have at least 3 or 4 more mutex. So in general, when you're using micro-ROS, you have 3 or 4 mutex in the RMW, and then you have 1 in the XRC EDDS library.
Okay, but this one, does this mean if we would access it from multiple threads, that at the end we have exactly this priority inheritance problem that Jan sketched? So let's say you have a low priority thread waiting for data, and a high priority thread not getting the lock. Okay. just as that we don't, let's say, that's why that's an important argument why we need this dedicated dispatcher thread with highest priority that, let's say, takes all the data from the middleware and distributes it.
Yeah.
Okay, thank you. Which is not a showstopper. I think that's a valid approach. It's just that we know why we do this.
Okay.
Thank you.
Thank you very much, Jan and Ralph, for hosting. And now is the turn of Bartolomé Ruiz. Are you ready?
Yes.
Bartolomé?
Ready.
Bartolomé Jimenez.
Yeah,
Sorry.
it's fine. I go by Bart.
Okay.
Yeah, I'll try to present as well. See how this goes. Yeah, so I'll do you guys see my screen?
Yes.
Yep.
Okay.
Yes.
So I'll just go like this and hopefully it will work. Yeah, so July last year, I think we presented about what we're going to do. So I think that this time they asked me if we had something interesting. I think we've been working quite a bit with eProsima as well. We worked in the last year on, we've been working actually with a lot of different threats, and we have faced the issue about the different priorities. And actually we run all the threads, I think, that are related to the micro-ROS part with the same priority. Maybe the fastest one is running a little bit higher, just as a side thing. As a quick thing for people that don't know our framework, our biggest asset is our frame. This is actually 2 prototypes before the current one, the current product that's out in the market. We are able to drive in really unconventional terrains without any problem. We can support payloads up to 100 kilos total, 50 kilos on top of the robot. We can drive. We haven't pushed it to the very limit, but in theory up to 100 kilometers with the 6 batteries that we can carry. And the weight distribution makes it so that all the 4 wheels are within the margins, the tolerance that we support. All the 4 wheels are always touching the floor, and it's a whole 4-wheel drive. This system itself, we have a very basic. This architecture is pretty much what still sustains. We have a main, what would be between the dotted lines is what represents the robot itself. In the red square, I've marked what communicates with micro-ROS. So we have what we call the HERCOS operation and control board. HERCOS is because of the model of the vehicle. And that one collects data from, talks to, in total, there's 10 different microcontrollers that are sending information over CAN open, more anything, to this operation and control board. And this operation and control board is collecting data like temperature, current consumption, humidity, errors on the devices, etc., etc., etc. And that's then either processed on the board, sent to higher levels to be used as information. We have ultrasound data that we use to navigate. We have power battery status and that we want to display. And all the control loop happens on the HERCOS operation control board, and that's where we are running our micro-ROS component, as I said. From last year when we showed, we had 4 nodes. Those 4 nodes were quite basic. We had 9 topics. Those 9 topics were published as subscribers. We had no services. We're not using services. We're still using Foxy. But we were using subscribers as services because there was some bug at that moment that we couldn't do it. And we were starting to look at diagnostics because we knew we had a lot of information that we had collected, and we wanted to push it to our higher system to be able to actually log that data and understand what's happening on the system when we're driving. From there to now, we have increased the amount of nodes, and we have actually now we have a lot of different services because it became they started to work quite nice. We have 8 different nodes. Actually, now that I'm thinking about, just based on the discussion, I could have showed a graph on how there's one node that is actually the one that creates the communication to the agent, and then all the other nodes simply have a way to talk to that node to receive the information they need to set up the other nodes. We use it's the RCL base or setup base, support base, or something like that. From the RCLC, if I'm not mistaken. And then move to Galactic. We've been there in Galactic for a long time, and we are also using the micro-ROS Diagnostics. I think that's the biggest recap that I can give from what we have. Now, the only thing that I regret not having here is a nice diagram about how the nodes are connected and the base and all those things. Maybe it would have been interested. But I want to talk more about the diagnostics component. For us, we've been using it quite a lot. It gives us really good information. It's the reason why we used the micro-ROS Diagnostics was because we wanted to use a package that we wanted to help a bit, but it became a little bit troublesome for us for different reasons. Really good, but at the same time, we had some complications on using it. For those who don't know, this is how the micro-ROS Diagnostics was the first design, at least when I started to work with it. We had one updater. The updater is basically a publisher that it's then connected to a node. And so you would have, if you have 3 updaters, you have 3 publishers. And in theory, the idea would be that each updater would talk with some type of application. So let's say a BMS or some motor controller or some other system, and that will get the data and publish to a micro-ROS diagnostic message. And the micro-ROS diagnostic message will then talk to the component that it's on the ROS2 side, that is the micro-ROS diagnostic bridge. And that information then will be published up. We managed to decrease the amount of there were strings. We changed how we map the micro-ROS diagnostic bridge with the tasks that are running, with the updaters that were running on the low level, but it wasn't on the embedded on the microcontroller, but it wasn't enough. So what we came afterwards was that instead of the footprint of one updater was bigger because if I wanted to have a lot of and actually this is probably a mistake on my slide. I need to change this, but there will be multiple application components to the tasks instead of having one updater per. This is what currently we have, and what we run, instead of running, you could still run multiple updaters, but instead of having one updater linked to only one application component, you can have one updater linked to n application components. That way you don't have that many, you don't have to create more publishers, and you can just have n tasks or n application components that can talk through the same publisher. Because before it was a 1-to-1 in this design, it was one task, one application. In this one, you would say that each task, it's one application component. So forgive me for the slide there. And then the micro-ROS bridge part would still be then the message would be published to the micro-ROS diagnostic bridge, and that information would then be taken by whomever needs to take it in the data that most default ROS nodes publish on the diagnostics, on the typical diagnostics topic. And this works. We use it. We have, just to give you an idea, we have about 75 tasks where we are getting data, but it has a lot of drawbacks, and sometimes it's about about a discussion that I also about something that it would be nice to discuss with what do the community think, if anybody else actually is considering using it, or if anybody has a comment on it. So first issue, each updater iterates over all the tasks every time, which means that if you have 75 tasks, and even though only one task needs to be updated for, let's say, one run runs every 1 second, another one runs every 100 milliseconds, and you want to update, right now you have to go through all of them anyways. Currently, we have to poll each task. So not only you iterate over each task, then you need to execute a task, and the task will then update some data, and you will publish that data. And then that also means that the amount of data that we're transferring is really suboptimal. We're not filling up the buffer on the middleware by any chance, which means that we're wasting a lot of processing time, or we are not taking advantage of the fact that we can run with static memory there. And then the diagnostics bridge, when on the diagnostics bridge part, it's really verbose on how one has to establish the whole map on the bridge. For some reason, yeah, the library that we use for YAML, it doesn't support. There's some type, I don't remember right now, but it's a way of using in YAML like include, so that you define one time a component, then you can reuse it in the rest of the file. Because there are some, in our case, we have some errors that are shared across different application components, and we have to repeat it on every one of the components just because of how we need to read the YAML. So an option is to change to another format that is not YAML, but maybe a Python type of interpreter or XML. Yeah, and then the same issue that we have, that we publish one task at a time. The bridge itself, it's receiving one task at a time, and then it just sends those immediately sends those tasks instead of buffering them and accumulating them, and just send one big message with an array of X amount of tasks. That means that we can flood. We have been checking our network stats. We have 100 megs. We use less than, I think, 150K. But still, it's something that definitely can be improved. And then the last one, Capra Robotics, we took the maintenance of the micro-ROS diagnostics, and we have had, fortunately, help from the people from Bosch or from Ralph. I've been asking him and bothering him a bit, but it takes some time because we don't use GitHub in our own organization. We don't use the structure. We're not used to all the ROS part, and some help there or more strict guidance would be really appreciated, so that we can actually help. We are willing to put the effort on maybe some of this on making this development if people seem interested. Otherwise, we need to reconsider what to do with the project itself, because I think it's really interesting. I think people can get good advantage of using it, but from our point, we are having some issues setting it up so that it's reliable enough for a person looking at it from the outside, that it's worth. And then one last thing, at Capra we do everything with C++. So having the code in C, it's not so much of a problem. It's just that for us to use everything that we for developers and for everything to just for anybody to jump, it would be easier to move everything to C++ if nobody else is using this micro-ROS controller, the diagnostics part, the micro-ROS diagnostics. But that's something that I didn't do it in the very beginning either, and I was not even considering, and it can easily be dropped more or anything because all the micro-ROS stack runs on C, except some of the applications. So that's my presentation. It was kind of short, but yeah.
Thank you very much.
Super nice. Just a couple of comments. First of all, it's nice to hear that you can rely on services now, because we know that they were like kind of unreliable in previous versions, but now microservices work pretty well, and also actions and parameters and all the thing that relies on services. And then regarding this C++ part, I think that this is a good point to discuss in the issue that Jan has in the RCLC about moving some parts of the stack to C++. So if anyone has thoughts or ideas, I think that the place to talk about this is this issue in RCLC.
Yes, exactly. So first of all, great that you took over the diagnostics package, and I'm sure. I mean, Ralph unfortunately had to leave now, but I'm sure he is most willing to help out, and don't hesitate to question him, right? Ask him questions and want to bring it forward. And as you know, some time ago, I put together all I made a review, what needs to be done if we want to have a C++ API. Essentially you could use, C from C++, and kind of minimalistic C++. There are some limitations like only having static member functions. You won't have the full C++ functionality available, but as in C, and the subscriptions has a context, and with the context, basically you have the capability of having access to the members of your class. So that's possible. But I think what you are asking, so basically to have a have RCL CPP for micro-ROS.
No, and that's maybe my mistake. It's all this. It's specifically for the micro-ROS diagnostics module. Yeah, for the RCLC, I think we had a discussion already last year, and it was okay with the context. Passing the context, we can live with that, so that we don't need to do a whole refactor or anything, and that's okay. No, here was about the micro-ROS, the diagnostics module itself, because Arne, if I don't remember the name wrong, is the one who started this, and I know you guys had the low level, like the embedded part with C, and then the diagnostics bridge with C++. But in our case, we do everything with C++, the embedded coding. So from our point, it would be easier to move the micro-ROS diagnostics completely into both components being C++, wrapping the RCLC calls that are needed. So that's the comment here.
Okay. Maybe best if you could just add maybe an issue, in RCLC, and propose, for then we can have a more detailed look on this.
Yeah, definitely.
What needs to be
or
done
I will follow
so that
up
it's being tracked.
I'll follow up on Slack with you, and then we can see if we put it on the micro-ROS diagnostics or the RCLC, the issue.
Yeah,
sounds good.
Okay, thank you very much. Very interesting. But now we have to follow up on the next topic. Tanmay, are you ready?
Yes. Yeah.
Yes, of course. So go on.
Let's see. You can see your presentation, yeah?
Yes, it's perfect.
So maybe retail automation is misleading, but basically I'm going to present how we're using micro-ROS on our mobile robot platform. I'll just introduce myself and the company and our product, and I'll show how it was before we introduced micro-ROS into our system and how it looks now, and just overview of how we've designed our hardware and software, the micro-ROS app itself. I'll show some videos and present some challenges that we face during when we introduce micro-ROS, and plans for the future. So basically, we're a robotics company located in Denmark. We do mobile robots for the retail sector. Currently, we have a pilot program with the Salling Group. They own one of the largest hypermarket chains in Denmark. So we're testing and deploying mobile robots into their stores, and that's our product on the right, Serena. So it's a differential drive robot with the 2D LiDAR and 2 3D cameras in front. So basically, we focus on transportation of goods using our mobile robot for online order fulfillment and restocking and just general movements of goods, because these retail stores tend to have like large footprints, and the employees spend a lot of time moving goods from either from the warehouse to the store, or picking products in the store for online order fulfillment. And that's where our robot comes in to help automate that. So basically, before we had micro-ROS, we just had our main computer on the robot, which is we use Intel NUC, and we use the standard ROS2 navigation stack. So it comes with planners and controllers and yeah, all our custom ROS nodes for our application. And we used a PCAN, like CAN dongle, to talk to our motor controllers. They're CAN open devices. And the main thing here to note is that the kinematic model control and odometry, everything lied on our main computer. But then we introduced micro-ROS. We're running it on on an STM board, and basically we still have our high-level sensors like the two 3D cameras and the LiDAR connected to our main computer, but we transferred the low-level navigation part onto the STM board. So the way that it works now is we pass on the local plan generated by the nav stack down to the STM board, and it's left to the microcontroller to move the robot. And it also, yeah, gives back fused odometry back to the navigation stack. And we run this at about 50 hertz. Yeah, and like the reason why we did this was to increase odometry and increase the accuracy of our odometry and the trajectory following, because what we find is that when we start to add things on our main computer, like 3D obstacle avoidance, the rate of things can drop, and that can cause the robot to sometimes miss a trajectory loop and start to oscillate, and then that kind of leads to a chain of events. So yeah, that's why we moved it down. And that's what it looks like on the robot. This is kind of a development robot, so it's not very clean. But yeah, we have the main computer on the left and the motor controllers on the right, and yeah, the STM board and the computer is connected through Ethernet. And STM controls the motor controllers through a CAN bus. So on the STM board, basically we have we kind of have like gatekeeper tasks for the CAN like traffic, and also like separate tasks for example, talking to the IMU, and they all kind of connect back to this micro-ROS app through free RTOS components like yeah, queues, and we also use semaphores and yeah, to coordinate between them. And it's all developed in C. Our entire stack is in Galactic right now, and yeah, and we use the Ethernet transport. So on the micro-ROS app, it's kind of standard. So we wait for the agent initially by pinging to it, and once we get a response, we know that it's connected to the agent, and then we create publishers, subscribers, standard stuff. And well, this is maybe not very elegant, but every time we spin some, we also ping the agent to check if it's still there. If it's not, then yeah, stop the motors, and yeah, it's kind of like added safety. Our two main update loops on our micro-ROS app is sensor fusion and odometry, and the trajectory follower, and they both run at about 50 hertz. So we implemented Pure Pursuit on the STM. So it's very similar to regulated peer pursuit that's on the navigation stack. So there's a look ahead point in front of the robot, and it finds the closest point on the local plan to follow. So it, yeah, so it kind of blindly follows the local plan. Yeah, and I have some videos. Let's see. So here, yeah, I just give a goal, and there's there's this blue dot in front of the robot, a red dot in front of the robot. That's the carrot point published by the SDM. Yep. I'll show another one. That's our robots at the store carrying the trolley. So the one on the right just undocked, so detached from the trolley and it's moving out. And it's kind of interesting to see how people don't react to it. They almost don't notice a robot. That's just the app. So you tell where the trolley is and where it has to be picked up and dropped off. You get the idea. So basically, so me personally haven't had a lot of experience with embedded development, so some things were not obvious. But maybe these are things that might help someone here. But basically, if you're publishing large messages, you have to take care of this Ethernet interface thread stack size. Yeah. Yeah, and initially we wanted the micro-ROS app, or like the node, to act kind of like a lifecycle node, which means that we needed services to work, but then quickly realized that it doesn't work with Galactic because it doesn't use fast RTPS. But we'll soon be moving to Humble, which does use this, so we might bring back services. Yeah, and having more than 4 ROS timers, you have to change this parameter in Qualcomm meta. And I also find having these VS Code extensions to be useful for debugging, and yeah, also these packages. So basically, we want to have the same firmware version on all of our robots, but only pass down the parameters of the kinematic model. So for example, wheel to wheel distance and the wheel radius might be slightly different for each robot. So I think once we move to Humble, we'll probably bring in parameters somehow. Yeah, I'm not sure. And we would also like initialization of entities like publishers, subscribers to be more robust. So maybe some mechanism to have the micro-ROS app like periodically announce publishers and subscribers, just to make it more robust. And we also want to introduce like error handling, maybe even look into diagnostics that Bart mentioned. Yeah, and we might also have another a separate ROS micro-ROS application on a separate board for hardware monitoring. So interfacing with the batteries and the actuator and other hardware components on the robot. And moving to Humble would probably take priority over everything. So yeah, that's pretty much it.
Okay, so thank you very much, Tanmay, for your presentation. Very, very interesting. And okay, for today, that's all. I want to thank you to all of us attending this meeting. And I hope to see you next meeting, that it will be not in October because we'll be at ROScon in Japan. It will be on November. So see you on next working group in November. Thank you very much, and bye.